the magnetic field lines outside a bar magnet are dash. Outside a bar magnet are dash. So coming to the bar magnet, it always having the poles are pair in form, that is north and south. Single pole may not exist. Okay, single north pole, single south pole may not exist. If you cut this also automatically, for example, if you cut this magnet like this, then this part is like north and south automatically created. This part is south, north automatically created. So that means two new bar magnets are created. And the magnetic field lines are called as flux, magnetic flux. These are flows from north pole to south pole. North pole to south pole like this. Here also north pole to south pole like this. But inside, to form a closed loop, they will be flow from south to north. So outside, so you can say outside, north to south, inside, south to north. Okay, so originate from the north pole and ends at its south. So the answer is option C. Coming to the next one, the materials which are weakly magnetized in the opposite direction. In the opposite direction, we have dia, para, and ferro. So these are diamagnetic or weakly magnetized in opposite direction. Okay, and these are also weakly but same direction. Same direction, opposite direction, same direction. These are strongly magnetized and same direction. Okay, so weakly magnetized, that permeability value is less than 1. Mu is permeability, ability to permit the flux, ability to permit the magnetic flux. Para, that is just greater than 1. Ferro, it is a strongly na, so double greater than the 1. Okay, so opposite direction, you can say that is the diamagnetic. So the answer is option D. It having somewhat of repel. Having somewhat of repel. Okay. Which are strongly magnetized. Just now I have given ferromagnetic. Those are strongly attracted. And coming to examples, paramagnetic examples is easily you can say all mediums. So like aluminium, platinum, chromium, all mediums, and M for manganese. Just remember like this one only, it is very easy. And one very important, that is nothing but is A, that is oxygen. Oxygen belongs to para. Hydrogen belongs to dia. Okay, so paramagnetic, here you can say aluminium. And it is very easy to remember the ferro also. Ferromagnetic material, just remember as nickel. Just remember as nickel. And N for nickel and I for iron, C for cobalt. Nickel, iron, cobalt are belongs to ferro. And those alloys. Alloys means steel, alnico belongs to ferromagnet. These are used to make permanent magnets. Why? Because these are strongly attracted now. So strongly magnetized. That's why. So para. And here copper. The best three conductors of the electricity are belongs to dia. Copper dia, silver dia. And iron is said to be nickel, iron, cobalt. Iron is said to be ferro. Coming to the next one. So diamagnetic. So in this diamagnetic example, all the best three conductors, silver, copper, gold. After that, you can say quartz, mercury. The gases we have hydrogen, and you can say zinc, and also antimony and bismuth. Antimony and bismuth. So these are the very important diamagnetic. So here quartz is there, you can use the quartz. Oxygen, para, all mediums, para, nickel, iron, cobalt, ferro. Okay, like that you can get the idea. Coming to the next one. Which are ferromagnetic? Just now I have given nickel, iron, cobalt. Nickel, iron, cobalt. So cobalt is given, so you can give the answer as cobalt. And permeability, I have already given permeability of dia. Dia is less than 1, greater than 1 for para, and very much greater than 1 for ferro. Okay. Coming to the next one, the relative permeability of the ferromagnetic material is 1000. So relative permeability given as 1000 and asking the permeability. So permeability mu is equal to mu naught into mu r. Okay, mu naught into mu r. Mu naught is the value that is 4 pi into 10 power minus 7 and mu r is given as 1000. So that is 4 pi into 10 power minus 4 Henry per meter. So the answer is option B. So the answer is option B. Okay, all of you clear? So mu is equal to mu naught into mu r. Mu r is the relative permeability. Mu naught is the absolute permeability, and that this is a fixed value. Coming to the next one, magnetism produced in these substances does not change with temperature. We have already discussed diamagnetic materials may not produce enough magnetism. So if you want to increase the temperature, decrease the temperature, whatever it may be, there is no change in this. So the answer is option A, diamagnetic. But coming to this para and ferro, they are producing some amount of the magnetism. So that's why if you increase the temperature, the magnetism produced may be decreased. Produced will be decreased. That means if you heat, magnet loses its property. Loses its property. It destroys its property. Okay. Here some drum sounds we are getting. Coming to the next one. The materials are used to make permanent magnets are dash. Already given ferromagnetic are used to make permanent magnets. So alnico, Marshall are ferromagnetic. So can do the answer as option D, all. But Maxwell is equal to dash numbers. Maxwell and Weber both are units of magnetic flux. Units of magnetic flux. Okay, so here 1 Weber is equal to 10 power 8 Maxwell. Okay, so 1 Maxwell is equal to 10 power minus 8 Weber. 10 power minus 8 Weber. So the answer is option A. So when a current carrying conductor is placed in a magnetic field, it experiences a force and it is given by dash. So if you have the magnetic field, yes, that is magnetic flux density B. If you place one current carrying conductor having length L, so current I, length L, and the angle between these two is, let us take theta, and the force experienced will be VIL sine. It is nothing but motoring principle. Motoring principle. And it is nothing but, let's say, Lorentz force equation. Now, no force is acts on current carrying conductor when it is placed. So, force is equal to VIL sine theta. Na? No force means 0. So, when it will be 0? It is possible whenever the sine theta tends to 0. So, when sine theta tends to 0, theta is equal to 90 degrees. 90 degrees means you can say, sorry, theta is equal to 0 degrees. 0 degrees or 180 degrees. So, when it will be happen 0 degrees or 180 degrees, whenever it is a parallel. That means both the conductor and magnetic field are in parallel. So, parallel to the magnetic field means no force. So, 0 or 180 degrees. The force exerted on the current carrying conductor or wire placed in a magnetic field is 0. Again, force is equal to 0. Then, angle between the direction of magnetic field. Just now we have discussed na, angle may be 0 or 180. So, 0 not given, so 180 given. So, can give the answer as 180. An induced EMF is produced when the magnet is moved into the coil. The magnitude of induced EMF does not depend on dash. The magnitude of induced EMF is BLV sin theta. So that means it depends upon big magnetic flux density, magnetic field strength, yes. And length or number of turns, yes, length or number of turns. And velocity or speed, so yes. But it does not depend upon any resistivity. So can you that it is not. So which is not they are asking now? Not asking. So that's why answer is option C. A positive charge is moving towards a person. The direction of magnetic field lines is dash. It is based on right hand thumb rule. According to this, if our thumb indicates direction of current, our fingers indicates direction of magnetic flux. Okay, that means, for example, all of you take your right hand and place like this. If the thumb is towards to upward direction, then curl fingers are in which direction? Take your right hand, then only you can understand. In which direction? Anti-clockwise. Okay, and it is down means clockwise. In the same way, this thumb gives the direction of current or charge. Okay, so this thumb is towards the person they are asking. So I am the person, so towards the person I have taken. Towards to the person I have taken. Okay, all of you see the video. Towards the person I have taken. Then curl fingers are in which direction? Anti-clockwise now. So towards anti-clockwise direction. Okay, if in case of away like this, then which direction? Clockwise direction. Okay, for example, if the thumb is upward like this, then you are getting clockwise. That means those curl fingers, 4 fingers now. So you are getting the concentric circle lines. So anti-clockwise. Thumb is upward, that is current or charge is upward. Okay, in case of downward direction, then also you are getting concentric circle, and downwards like this, that is clockwise. Direction. Okay. Coming to the next one, the shape of magnetic field lines produced by current carrying conductor. Just now we have discussed, now the shape is nothing but concentric circles. An electromagnet is consist of long coil insulated copper wire wound on the soft dash. Let us take a soft ferromagnetic. Ferromagnetic is nothing but than say. Here, let us take iron, cobalt, nickel, and we have to take some insulation on that. Okay, upon this, we can say this wiring is nothing but can say copper. Okay, so that is iron core. Iron core is used. Okay, coming to the next one. According to Fleming's left hand rule, thumb indicates dash. Here, left hand rule or right hand rule indications are same. Here, thumb will use the direction of motion, that is movement. Middle finger, I for eye, current. Forefinger, F for field, magnetic field. That means if you take your left hand and if you take the 3 fingers of forefinger, middle finger and thumb mutually perpendicular to each other. Okay, forefinger shows magnetic field, middle finger shows the current, thumb will give the direction of the motion, direction of the force or direction of the motion. And this left hand rule is used in case of motors. Okay, so here they are asking thumb, direction of the motion or force. So then you answer as option C. The direction of motion in motor is given by dash. So in motor, we use left hand rule. Okay, in generator, so R, 2 R's are there now, R domination. So right hand rule. Like that you can simply remember. Just a remembering trick. Okay, and in motor, we need to find out the direction of motion. Or force that is given by thumb. In generator, what is the output? Current. direction of current, that is given by middle finger, I, given by middle finger. Okay, so I have already given this in the previous session. So the direction of motion in motor is given by dash rule, motor left hand rule. Okay, coming to the next one. According to Fleming's right hand rule, the middle finger indicates dash. Just now I have given indications of fingers are same. So forefinger gives F for field. Field in the sense magnetic field. Okay, middle finger I for I, current or EMF. Okay, and thumb will give direction of force or motion. Direction of motion, which direction, clockwise or anti-clockwise? So middle finger they are asking I for I, current. So we can give the answer as option B. Coming to the next one, the direction of current in generator is given by dash rule. The direction of current in generator is given by dash rule. So generator, which rule we are using? R, 2 R's, R are dominated. So I said Fleming's right hand rule. Who among the following scientists is credited for discovering the phenomenon of electromagnetic induction? Electromagnetic induction, that is given by Faraday. Faraday's law of electromagnetic induction. Electromagnetic induction. Okay, so the answer is Michael Faraday. Michael Faraday. Reluctance is the ratio of dash. We don't know about the reluctance, but we know very well about the resistance. Okay, resistance which opposes the flow of current. In the same way, reluctance also which opposes the flow of flux. So I want to give small comparison between electrical and magnetical. So in electrical, we have the current. Flow of electrons is said to be a current. In the place of current, here in the magnetic, we have magnetic flux. So the flow of magnetic field lines is said to be a flux. Why? Units of current, amperes. Flux, Webers or Maxwell. Okay. And to flow the current, we require voltage or EMF. We require voltage or EMF. Nothing but the difference is EMF is the gross value, voltage is the net value. Okay. It is an open circuit. It is on the connected to the load. So voltage or EMF. It is the electromotive force required to move the current. In the same way, here MMF is there. It is the magnetomotive force. Motive force to flow the magnetic flux. It is magnetomotive force. That is, it is a force required to move the magnetic flux. Okay. And this MMF is equal to product of number of turns into current. Number of turns into current. So units are ampere turn. Units are ampere turn. In the same way, here we have the resistance is there. Resistance is nothing but voltage by current. Opposes flux, opposes the current. So inversely proportional to the current. In the same way, reluctance is in the place of voltage, we have MMF. So MMF. In the place of current, we have flux. So inversely proportional to the flux, and reluctance is equal to MMF by flux. So like this, if you are going to compare, then you can easily understand. Current plus flux, voltage plus MMF, or EMF plus MMF, resistance plus reluctance. Okay, and units are MMF, ampere turn, flux Weber, ampere turn per Weber. Okay, coming to the next one. If you want once again, you can watch again. Okay. So if a coil has 200 turns having a current of 2 amps, produces the flux of 100 Webers, then reluctance of the coil is dash. Reluctance of the coil is dash. Just now we have discussed about the reluctance, MMF by flux. MMF, product of number of turns into current by flux. Okay, and here also the unit also they have given ampere turn per Weber. So ampere means 2 amp, or current is 2 amp. Number of turns are 200 turns by flux is 100 Weber. So 100 once, 100 2, that is something you can say 4. The answer is 4 you are getting. So the answer is 4 you are getting. Coming to the next one. If a coil has 400 turns having current of 2.5 amps and reluctance of 10 ampere turn per Weber, then flux produced by the coil is dash. So same formula, reluctance is equal to mmf by flux. So substitute all the values, reluctance given 10 ampere turn, mmf, product of number of turns into current, and asking the flux. 25 into 4, so the flux is equal to 25 into 400. So 100 is the answer. So the answer is option. Okay. Other numericals. If a solenoid has area 10 meters square and having a current of 2.5 amps and reluctance given 10 ampere turn per Weber and flux produced by the coil is 100 Webers, then what about the flux density? Flux density. So all of you try to get this flux density. Flux density is nothing but flux by unit area. Flux by unit area. Flux given 100 Weber and area given 10 meters square. So you are getting 10 Weber per meter square. And we know 1 Weber per meter square is equal to 1 Tesla. 1 Tesla. So 10 Tesla. 10 Tesla. Okay, so the answer is option B. 10 Tesla, answer is option B. That means they have given this I and reluctance just to confuse you. We no need those two. Okay, coming to the next. A coil has 500 turns and resistance is 20 ohms is wound uniformly on the iron ring of the area 4 centimeters square connected to 24 volts AC supply and relative permeability is 800. Then mmf of the coil is dash. In the previous session also have given mmf of the coil is number of turns into current. So they have given the turns, that is 500, but not given the current. Current is equal to voltage by resistance. They have given 24 volts DC, substitute that one, and resistance 20 ohms. Okay, so substitute that one, 24 by 20. So you are getting 600 now. The answer is option B. 600 ampere turns. That is the answer. Coming to the next one. Coming to the next one. A 10-meter length of the solenoid has 400 turns with a current of 2.5 amps flowing through it. Then magnetizing force required. Magnetizing force. Magnetizing force. Magnetizing force or magnetic field intensity. Magnetic field intensity or magnetic field strength. Magnetic field strength is given by H, that is equal to mmf by length. mmf by length. mmf is nothing but product of number of turns into current by length. Number of turns 400 into current 2.5 by length 10 meter. So 25 into 4, that is 100. So you are getting the answer is 100. So the answer is 100. Okay. Coming to the next one. Coming to the next one. Units of magnetic field intensity or magnetic field strength H is equal to dash. Just now I have given now H is equal to mmf by length Ni by L. So N, I ampere, N turn by length means meter. Ampere turn per meter. So the answer is option D. Ampere turn per meter. So the answer is option. I state is the unit of test. I state is the unit of test. So H units are nothing but when say ampere turn per meter and another unit is nothing but when say Eirsted. So to give the respect to the scientist, they have given Eirsted is one of the unit of this magnetic field strength. and units of flux density. Just now I have given the flux density, flux by unit area, flux Weber, area meter square, Weber per meter square. 1 Weber per meter square is nothing, you can say 1 Tesla. Weber per meter square. Coming to the next one, 1 Tesla is equal to dash. 1 Tesla is nothing but 1 Weber per meter square. North pole of a magnet can be identified by dash. So let us take one option by using the iron fillings. Okay, so if it is a magnet, it has north pole and south pole. If you have placed the iron particles, these iron particles equally attracted by north pole and south pole. Equally attracted by north pole and south pole. So we cannot find out now which is a north and which is a south. Why? Because equal attraction. So can eliminate. If you use any iron bar, it is just attracted by magnet. So we can't identify which is the north and which is the south. And let us take another magnet. In that poles are not marked. Poles are not marked. Then if you are getting attracting, if you are getting attracting force, then what you can say, another one may be north, then only there is a opposite poles attract. If there is a repulsive, then you can say it may be a south. So there is a two possibilities, two poles, two possibilities means we cannot identify. So the remaining option A. So for example, if you take any other magnet, okay, if you take any other magnet, here it has poles are marked north south like this. Whenever you can say here north south, and if you want to identify the poles of any one magnet, so whenever you place very near to each other, here it is a north pole. If there is a attracting force means it must be having south. So if it is a south, another one is a north. So we can identify now. If you are getting repulsive force, then here N means here also N, here N means here also S. So you can identify the poles. So we can identify the poles if you have any other magnet that having its poles marks as the north and south. Okay, so the answer is option A. Coming to the next one. A bar magnet is immersed in a heap of iron fillings and pulled out. The amount of iron filling ranging to the dash. Just now we have discussed north pole is equally attracted to the south pole. So both are almost the same. So north pole is almost equal to the south pole. Both are having the same attraction. Both having the same attraction. Coming to the next one. Units of permeability. Units of permeability. Permeability I have already explained in the previous class. Permit ability. It is the ability to permit the flux. Ability to permit the flux. Okay, it is the ability to permit the flux. Okay, so the permeability is denoted as mu, and mu units are Henry per meter. Henry per meter. So the answer is option B. If they are asking permeability of free space, or absolute permeability, denoted as mu naught, that value 4 pi into 10 power minus 7 Henry per meter. It also having the same unit. And here we have the relation mu is equal to mu naught into mu r. What is this mu r? Relative permeability. Mu r is equal to mu by mu naught. So mu having Henry per meter, mu not having Henry. So both will be cancelled. So this mu are having no units. Okay, mu are having no units. So if they are asking permeability or permeability of free space or absolute permeability, units are Henry per meter. Okay, Henry per meter. So units of relative permeability. Here they are asking relative permeability. Just now I have given it has no units. It has no units. Units of permittivity, epsilon. Where we have this epsilon in the capacitance, C is equal to epsilon A by D. So epsilon is equal to C into D by A. Okay, and epsilon is equal to C capacitance farad, D distance meter, area of meters. 1 meter get cancelled out. Epsilon units are farad per meter. Epsilon is nothing but farad per meter. Okay, so farad per meter answer is option A. Coming to the next one, units of relative permittivity. In the same manner, epsilon is equal to epsilon naught into epsilon r. Epsilon r is the relative permittivity. Relative permittivity. And epsilon r is equal to epsilon by epsilon naught. It is also farad per meter. It is also farad. Both are cancelled out, means you can say no units. You can say no units. So relative permittivity having no units. Having no units. So the answer is option D. Coming to the next one, units of permeance. Units of permeance. What is this permeance? Reluctance means opposes. Permeance means permits. Permits the flux. Allowance. Reluctance opposes. So permeance is reciprocal of reluctance. Okay, like conductance is reciprocal of the resistance. Now, same like conductance is reciprocal of the resistance. Same like here also. Permeance is reciprocal of the reluctance. Reluctance units are mmf by flux, ampere turn per Weber. So here Weber per ampere turn. Weber per ampere turn. So the answer is option C. So the answer is option C. Okay. Just to the first question. Gilbert is the unit of dash. Gilbert is also one of the unit of magnetomotive force, MMF. We know very well MMF is equal to product of number of turns into current, and the units are ampere turn. Ampere turn is one unit, and also Gilbert is the another unit. Another unit. Coming to the next one. Magnetism of a magnet can be destroyed by dash. How we can destroy the magnetism of a magnet? If you are going to increase the temperature, that means if you are going to heat, then also magnetism of a magnet can be destroyed by hammering. That means if you hit the magnet, then also its magnetism is going to be destroyed a little bit, and by inductive action, by opposite action of the another magnet also can destroy the magnetism. And that means we can say we can destroy by all of the above methods. So we can give the answer as all the above methods. Coming to the next one, a bar magnet is divided into two pieces. Which of the following statement is true? So I already said in case of bar magnet, poles are always pair informed. Okay, poles always pair informed. Okay, that means single pole may not exist. single pole may not exist. Okay, so if you cut the magnet into two pieces, you will get like this. And yes, another side south pole is created. Here another side north pole is created. That means it will be work as a one magnet. It will be work as another magnet. That means you can say two new bar magnets are created. So if you cut into two parts, two new bar magnets created. If you cut into three parts, three magnets created. Four parts, four magnets are created. Single pole not exist, automatically another pole is created. The ability of a material to remain magnetized after removal of the magnetizing force. If you apply the magnetizing force, it is going to be magnetized, and if you remove that force also, it remains some amount of the magnetism. That retained property, that remaining property or that retained property, some of the magnetic property it left in it. So that property is nothing but we can say retentivity property. It retains some amount of the magnetism. That retained property is nothing but retentivity. The compass needle cannot be used to detect dash. Compass needle cannot be used to detect dash. We know very well about the compass. It shows the direction of north and south. It shows the direction of north and south. Okay, so compass needle cannot be used to detect. It shows north and south direction, means magnetic north and south direction, and it also shows the polarity of a magnet. Yes, polarity north pole, south pole, and it also gives the direction of the magnetic field from north to south, but it may not give the strength of the magnet. So we can give the answer as option C. We can give the answer as option C. Coming to the next one, the ratio of intensity of magnetization to the magnetizing force is known as dash. What is the ratio of intensity of magnetization to the magnetization force? That is nothing but we can say susceptibility. Susceptibility is nothing but the ratio of intensity of magnetization to magnetization force. Which of the following device converts low voltage alternating current into high voltage alternating current? So from low voltage to high voltage, that means voltage changing. That is nothing but we can say transformer. So transformer step up the voltage, that means increase the voltage, and it can step down the voltage by keeping the power as constant. Keeping the power as constant. Okay, so the device is considered as a transformer. It transfers the power from one circuit to another circuit by increasing the voltage or decreasing the voltage as per our requirement. Transformer works on the principle of dash. It works on the principle of Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. In this particularly you can say mutual inductance. Mutual inductance. Okay, so transformer works on the principle of mutual inductance or mutual induction. Coming to the next one, generator works on the principle of Faraday's laws of electromagnetic induction. So the answer is option B. So we have completed a lot of questions in this magnets and magnetism. We will discuss remaining in the next session. In the next session, we will take another topic